So I'll be talking to you today about SENIC, a scalable NIC design for end-host rate limiting. So this is joint work with several colleagues, Yilong, Vimal, Abdul, George, and Amin, several of whom are also present here in the audience. So data centers are huge infrastructures that cost hundreds of millions to billions of dollars. And they use heavy statistical multiplexing to make effective use of this underlying infrastructure. So essentially, you have several different services, applications, or tenants that are sharing the same underlying infrastructure. And the emergence of cloud services like Amazon EC2, Google Compute Engine, etc., is further evidence of this trend. And when you have such sharing of the underlying physical resources, resource management and allocation is extremely important. And in particular, we are concerned about network resource management in this talk. So as you can imagine, there have been a number of different proposals for doing network resource allocation in the data center. So in the performance isolation space, you have proposals like Octopus, Seawall, IQ, etc., which essentially try to isolate the performance that is achieved by each individual tenant in the data center. And similarly, congestion control raises challenges of its own in the data center due to the high bandwidth, low latency network, as well as the bursty nature of traffic. And again, there have been a number of different proposals to perform congestion control in the data center. So we looked at all of these different proposals, and one thing we realized was that they all rely on an underlying substrate of programmable rate limiters. And perhaps more importantly, the underlying substrate of rate limiting needs to be extremely scalable. So in particular, servers today need thousands of rate limiters on each physical server to support these needs of performance isolation and congestion control at a per flow level in the data center. So given this need for scalable rate limiting, let's see what are the options we have today for rate limiting in physical servers in the data center. So on the one hand, we have software approaches, such as the Linux queuing discipline or essentially different operating system support for rate limiting on the host. So this easily scales to support thousands of classes. However, the downside is that, as you can imagine, it doesn't quite work very well at high link speeds. So the CPU utilization for this is very high, the CPU overhead, and it's not as accurate or precise as you would like it to be. Definitely not as accurate as hardware-based approaches. And the other downside of the software-based approaches is that it precludes us from using recent NIC advancements such as SRIOV and hypervisor bypass. On the other hand, if we look at hardware approaches, essentially some modern NICs support rate limiting natively in the NIC hardware. The downside of the hardware approach is that it doesn't really support a lot of classes. So typical NICs support on the order of few tens of traffic classes that can be individually rate limited. However, the hardware has several other good properties, such as it works well at high link speeds, and it's able to lower the CPU utilization because all of the packet scheduling task is offloaded to the NIC. So that brings us to SENIC. So with SENIC, we wanted to design a NIC that can essentially provide you this scalability of the software approach while offering all the other benefits of the hardware approach, such as working well at high link speeds and having low CPU overhead. And in the rest of this talk, I'm going to tell you how to reorganize the responsibilities of the NIC and the operating system to achieve this goal. Let's begin by taking a look at how the transmit data path looks in a current state-of-the-art server. So here we're essentially depicting the boundary between the host and the NIC. So I want to point out that there are essentially two kinds of memory through which a packet passes through along the transmit data path. So in particular, the host uses DRAM, which is cheap and abundant. On the other hand, the NICs use SRAM, which is very fast. Unfortunately, it's expensive and limited in the NICs. So now let's take a look at how a packet gets transmitted in such a data path. So we have several queuing discipline queues, or essentially operating system managed queues, one for each traffic class in the host memory. And when the operating system needs to transmit a packet, it essentially notifies the NIC about a packet that's been enqueued into one of these queues. The NIC then schedules a DMA transfer, first of packet descriptors and then packets, into internal TX ring buffers in the NIC hardware. So this is essentially what's in SRAM. Subsequently, there's a packet scheduler on the NIC, which is going to rate limit these individual NIC TX ring buffers. So it's going to compute the schedule of packet transmissions from the NIC and eventually transmit the packet out on the wire. Now, if we step back and look at this design, let's try to identify what the current architecture gets right and what are the challenges to scalability that we have with this design. So host DRAM is cheap and abundant, and essentially you can store lots of traffic classes or per class queues in host memory, and this is good. So hardware is really good at per packet scheduling, maintaining fine-grained timers, and essentially per packet operations that are offloaded from the CPU. And so having the packet scheduler on the NIC is really good because you can achieve very accurate rate limiting even at high link speeds. Now when we look at the transmit ring buffers, this is where the challenge to scalability really lies. So NIC SRAM is expensive and limited. And as a point of comparison, so the Miricom NIC supports about 2 megabytes of SRAM for all state on the NIC. So this includes packet buffers, descriptor rings, protocol state, state that's used for the scheduler, metadata, etc. And there is essentially no way to scale this to support thousands of classes without making the NIC too expensive. So the key question we ask here is, can we get rid of these large buffers, the TX ring buffers? And that's essentially what we do with the SENIC design. So with SENIC, we have a number of per class queues that are stored in the host memory in DRAM, which scales really well. And you have the packet scheduler on the NIC, which is essentially going to schedule packets directly out of these per class queues that are stored in host memory. Now let's take a look at how basic packet transmission works in such an architecture. And later we'll look at more other features that NICs need to support, such as segmentation offload. So as in the traditional NIC design, when a packet needs to be transmitted, the operating system notifies the NIC about the packet that's been enqueued into one of these queues that are stored in host memory. Now the packet scheduler on the NIC directly rate limits these per class queues that are stored in host memory. So it's going to schedule a particular packet from one of these queues for transmission. So it's only after scheduling this packet that we DMA the packet from the host memory to the NIC and eventually transmit the packet out on the wire. So SENIC is all about this late binding of packet transfers to the NIC. So we first compute the schedule of packet transmissions and subsequently DMA the packet from the host memory for transmission. So now to reiterate what we achieve with the SENIC design, we store these per class queues in host memory, which helps us achieve scalability to thousands of traffic classes. And we have a dedicated packet scheduler on the NIC in hardware, which enables us to achieve very accurate and precise rate limiting with low CPU overhead. And in this design, the CPU essentially handles all control plane operations and infrequent operations. So things like configuring queues, rate limits, or classifying packets, etc. So the CPU is essentially free to batch operations and is not involved in the actual data path while transmitting the packet, in particular for packet scheduling. So we went ahead and built 2 prototypes of SENIC. So the first is a NetFPGA 10 gigabit hardware prototype. So this demonstrates the feasibility of building such a NIC in hardware. So this prototype implements a simple token bucket scheduler, and it actually implements the late binding of DMA transfers from the host memory to the NIC that I just described. The second prototype that we built is a software prototype. So in this software prototype, we essentially dedicated one CPU core on the system for just the network scheduling task. So this is a CPU core that's just spinning continuously and just computing the packet schedule for transmissions. So we don't schedule any other applications on this particular core. So in that way, we're able to offload all the network scheduling tasks to this particular CPU core. And this works with any existing NIC. It's essentially a kernel module which does packet scheduling and transmits the packets on the wire with a dedicated core for the scheduling task. So first, I'll describe some microbenchmarks that we ran with our NetFPGA 10 gigabit hardware prototype. So this was synthesized at 100 megahertz with 1,000 hardware rate limiters. This is at least one order of magnitude more than what's commercially available, such as with, for example, the Intel NIC, which supports about 128 hardware rate limiters. So the first key question that we answer is the rate limiting accurate? So to measure the accuracy of SENIC, we looked at the inter-packet delay for packets that are transmitted from a particular traffic class. So in particular, when you have a traffic class that's configured with a certain rate limit, and when you know the packet size, you can compute the exact departure times of packets from that traffic class. And we essentially computed this sort of schedule for an ideal pacer, and then compared it to our measurements from our prototype. And we essentially saw that the average inter-packet delay was within 0.038% of an ideal packet pacer, showing that SENIC is extremely accurate. And at the same time, the standard deviation was also very low, showing that it's extremely precise and there's no jitter in enforcing these rate limits. So the next key question that we answer is it fast? Can SENIC actually keep up with high link speeds? So the key question that determines how well SENIC works at high link speeds is how quickly we can compute the packet transmit schedule. And in particular, the time to make a scheduling decision, the time to schedule one class and then move on to compute the schedule for another class. So with our prototype, this required 5 SRAM lookups, which is essentially 50 nanoseconds at the 100 megahertz clock rate. And to give some context here, the time to transmit an MTU size packet at 40 gigabits per second is 300 nanoseconds. So the 50 nanosecond scheduling time is well within the budget to transmit, to pipeline the scheduling task along with packet transmissions. And of course, when you want to support smaller packets, SENIC essentially schedules a burst of packets from a particular class at a time up to a certain maxed number of bytes for that traffic class. So we also ran some macro benchmarks with SENIC using the software prototype. And in particular, we wanted to look at how it can isolate different tenants that are sharing the underlying infrastructure. So this figure depicts a server where we had 10 Memcached tenants. So each of these is a Memcached server. And we had a 6 gigabit per second total rate limit that was configured across all of these Memcached tenants. So this was essentially split equally among the Memcached tenants, and again further divided equally among the respective tenants' individual flows. So the server also had another UDP tenant, which was trying to send traffic as fast as possible. And this UDP tenant was configured with a rate limit of 3 gigabits per second. So this setup was essentially replicated across 8 machines. So in case of Memcached, we have 1 Memcached server per tenant, and 7 Memcached clients for each tenant that are spread across these 8 different machines. And in case of UDP, it's essentially one application per server and all across the 8 machines. And it's essentially sending all-to-all traffic between the UDP tenant applications. So the key metrics that we wanted to look at here are the tail latency for Memcached, which is a latency-sensitive application, and the throughput that's achieved by UDP. So how close can it actually achieve compared to the configured rate limit? So we compared SENIC to 2 existing software-based rate limiting approaches. So one is hierarchical token buckets, or HTB, which is kind of the de facto standard that's available in Linux today, and it's used very popularly. And the second approach is parallel token buckets, or PTB, which was proposed more recently. And it essentially takes hierarchical token buckets and makes it more multi-core friendly. So removes some of the lock contention, etc., by having fine-grained locks, and essentially improves upon the throughput that hierarchical token buckets can actually achieve. And we essentially ran these experiments by varying the load that was generated by the Memcached tenant. And we had the UDP tenant generating a constant load in the background. And we only had a configured rate limit for the UDP tenant. So let's first look at the Memcached tail latency. So this graph depicts the 99.9th percentile latency that's observed by Memcached as we vary the load along the x-axis here. So this is the load generated by the Memcached clients on the respective Memcached servers. And essentially, we vary the load from 20% all the way very close to 100% of the configured 6 gigabit per second limit. And as you can see, SENIC has significantly lower latency, as well as it's able to sustain much higher requests per second or much higher load compared to both HTB and PTB. And in particular, I want to point out here that SENIC was able to sustain a tail latency or 99.9th percentile latency of 4 milliseconds for Memcached, even at a 97% load. And remember that this is all, again, with the background of 3 gigabits per second of UDP traffic that's also running concurrently. So this next metric we looked at was the UDP tenant throughput. And remember, the UDP tenant was essentially configured to have a max rate limit of 3 gigabits per second, which was split equally among the different flows. And with SENIC, we see that it's able to achieve very close to this configured rate limit, whereas both HTB and PTB have trouble keeping up with this rate limit, regardless of the load that is actually generated in the background by the Memcached tenant. So the takeaway here is that SENIC can accurately enforce rate limits and also simultaneously deliver high throughput. So with Memcached, we saw that it's a latency sensitive application and it was able to successfully have low latency. And this was completely isolated from the performance of the UDP tenant, which was also running in the background and was able to achieve high throughput as configured here. So we saw that SENIC offers promising performance. Now let's look at some other NIC features that are available in some modern NICs and that SENIC must also support. So SENIC supports several such features, such as TCP segmentation offload, hypervisor bypass, as well as a packet scheduler on the NIC. So in the interest of time, I'm only going to cover TCP segmentation offload. So the design of SENIC influences how several of these features are actually going to be realized on the NIC. So to give some background, TCP segmentation offload, or TSO as it's more popularly known, is an optimization where the host operating system can essentially hand off a large TCP segment up to 64 kilobytes in length directly to the NIC for transmission. So this TCP segment consists of a single header followed by several MTU-sized segments. So the NIC is tasked with splitting this up into individual MTU-sized segments that are eventually transmitted out on the wire. And the way the NIC can do this today in existing NICs is that the NIC can fetch the header once, cache it on the NIC, while the entire TSO segment is being processed. So with SENIC, we wanted to enable the interleaving of packets from different traffic classes so that we can avoid line rate bursts of packets from a single traffic class. So this ensures that the rate limit is enforced very accurately, even at small timescales. So with SENIC, we essentially support thousands of traffic classes. This means that storing or caching the header for each of these classes on the NIC would be really expensive. And the way we get around this in SENIC is by essentially DMAing the header and the payload for each MTU size segment that's transmitted out on the wire. So the NIC essentially does not cache the individual headers for the TSO size segment. Well, this means that we're actually doubling the number of DMA transfers that are actually required while supporting TSO. So the natural question to ask is this going to be a bottleneck? Is it going to limit the maximum throughput that you can sustain with SENIC? And the short answer is that this is not going to be a problem. And the reason is that modern systems are already capable of sustaining much higher number of DMA transfers per second than what we need to support TSO. Let me give some concrete numbers here. So at 40 gigabits per second and a 1500 byte MTU, SENIC requires about 6.5 million DMA transfers per second to transfer both the header and the payload. And we ran some measurements on a Mellanox 40 gigabit per second NIC, and we saw that it was already able to sustain 13 to 14 million DMA transfers per second from different locations in memory. So this means that SENIC can essentially support the required 6.5 million DMA transfers per second with existing technology. So this shows that essentially SENIC is not going to be limited by the performance of the underlying DMA subsystem. So to summarize, SENIC delivers on the vision of scalable rate limiting on end hosts. So SENIC is a scalable rate limiting substrate that's also accurate and precise even at high link speeds. And it's easily implementable in both hardware and software. So the code for both of our prototypes as well as all the experiments we ran is available at this link shown here. And finally, a small message. We are hiring at Forward Networks. So if you're interested, please come talk to me. Thank you all for your attention.
Any questions? Okay. So I have a quick question.
Yeah.
So your hardware is on NetFPGA, right?
Yes.
So have you thought a little bit about how is it different, or how is it easy to implement this on like commodity NICs? Like, oh, say everybody seems to use Intel 82599.
Right.
What would it take for that NIC to support SENIC?
So most of the pieces that we use already exist in commercial NICs. So for example, the packet scheduler already exists. They already DMA packets. And essentially what we need is to reorganize the pipeline a little bit. So packets already exist in host memory today, and the NIC is just copying it once into its internal ring buffer. And what we are doing is delaying this transfer of the packet. So what we essentially need is a scalable scheduler, and which we further describe in the paper, and the ability to pull these packets on demand from host memory for transmission.
Okay, cool. Any other questions? Okay. Let's thank the speaker again.
Yes.